Thank you so much for reminding me to record. All right, so we were saying that in the case, sometimes we have situations where we need to calculate values and then we're not using, for example, a ruler. Say we're not using a ruler. So in order for us to get that uncertainty value, right, that we need, we have to go through error propagation, and that's exactly what we're going to do now. So we wish to determine the elastic constant of a spring using Hooke's law, right? Let's use this example with its actual uncertainty. All right, so we want to find the value. We want to find the value of K, right? We want to find the value of K, and we also want to find, right, our uncertainty. All right, so that might look funny at first, but just give it a few minutes, give it a few seconds, right? Let me write it in a different way. So remember, we spoke about length and we said we wanted to find length and the uncertainty in length. So length could be the uncertainty length. This could be this could be 0.1, right? So this and a more easier way that we could put it is, for example, um a more easier way, or sorry, an easier way, sorry, we could put it is plus and minus, right? So this particular thing, have ever seen this before?
No, sir.
You have never seen this before? This triangle here,
Yes,
right?
sir. It's before.
All right, you remember what it means,
Yes, sir.
right? And what does it mean?
Delta.
Right, so this is delta,
That
and it means a change, right? A change in a value, right? So for example, we had an initial temperature of 20 and we saw a temperature raise to 30. Delta T would be equal to what? What would delta T be equal to? Right,
10.
right, so 10.
10.
Right, so the difference between these two. All right. Okay, so we wish to determine the elastic constant with its actual uncertainty. So the uncertainty in K can be found if the uncertainty in F and X are known, right? So we need to be able to find, we need to be able to find the uncertainty for F and X for us to be able to find the uncertainty for K. All right, so we'll now go to some rules which govern error propagation, right? So the rules of error propagation can be readily derived from calculus, and in this topic, we shall denote Q as the quantity we wish to determine, right? Delta Q as our uncertainty, right? Uncertainty value, that error, right? Uncertainty or error of the quantity Q being measured. All right. Uh, sorry, my grammatical errors. All right, please excuse me. So the fractional uncertainty would just be delta Q over Q. And then we can use the fractional uncertainty to find our percentage uncertainty so that we can say it has a 10% error, it has a 1% error, it has a 2% error, right? We can use this. This gives us a better idea of the amount of our error. And we can also use this in our labs to determine our accuracy and sorry, not accuracy, precision. Precision, right? So if we're calculating, if we're doing an experiment to determine the acceleration due to gravity and we find our acceleration due to gravity as 9.7 plus and minus 0.3, right? We would say 0.03, right? This would be our fractional uncertainty. We can use this to find our percentage uncertainty, and then we can say that it has an uncertainty of 3%. Right? That's just giving you an idea. All right. So are we clear so far?
Yes, sir.
All right. We're clear. Okay. If you have any questions, please stop me. Please interrupt me. All right. Please interrupt me. Okay. The first one, rule number 1. If two quantities A and B are multiplied together, the maximum fractional uncertainty of the product is the sum of the two fractional uncertainties of A and B. So if you have a ruler and it has A, we're using a ruler, and it has a uncertainty of 0.01 or 0.1 centimeters, as we have seen before, right? 0.1 centimeters. And B, we're using a, let's say a triple beam balance, and it has an uncertainty of say 0.1 kilograms, right? 0.0 or 0, that's too big, 0.01 kilograms, right? That's still too big, but it can work, right? We would put 0.01. This is the change in A and the change in B, right? So we want, let's, for example, it's just an example, it's not an actual experiment, right? But for example, we want to calculate our uncertainty. We put change over A over the actual value for A, and then the change over B, which is 0.01, over the actual value that we measured for B. Is that clear? Are we understanding this? All right, let me go over it again. Should I go over it again?
Yes, sir.
All right, so we are using a ruler, right, for A, ruler, and we are using a triple beam balance to measure the mass, right? Triple beam balance and a ruler, right? And let's just say A is mass, A is the length, and B is our mass, right? A is length and B is our mass. No, we would use the uncertainty of A from the measurement to find the complete or the maximum fractional uncertainty. The complete uncertainty for both of them, right? In order to find Q. Q is just a random value, right? It's not an actual thing. Or probably, all right. Yeah, let's work with this. Let's work with this one, right? So we would use the uncertainty for A, 0.1 centimeters. We would divide 0.1 by the value that we calculate. So say we found the length to be 10 centimeters. It would be 10 plus or minus 0.1 centimeters. Now, for the fractional uncertainty, you would have, so let's just say length equal 10 plus and minus 0.1 centimeters. The fractional uncertainty change in L over L would be, what would this be? Someone please help me, right? What's the change in L? What's the uncertainty for this particular quantity here? Hello, you hear me?
So 10 plus 0.11.
Right, so we were now trying to find the fractional uncertainty. So what is the uncertainty value? 0.1, right?
Yes, sir.
Yes, sir.
Yeah, 0.1. And then the actual value that we calculated was 10, right?
Yes, sir.
So this would be equal to what?
1.
0.1 divided by
No,
10.
no. 0.01.
Right, so our fractional uncertainty would be 0.01, and we would do the same thing for B. Let's just say it is mass. We would do the same thing, so you'd have 0.01 over whatever value that you got for your mass, and then with the addition of those two would give you the uncertainty, fractional uncertainty for Q. Is that better now? You understand now?
So I can understand some part of it, but kind of lost. I'm not coming across with.
Okay. All right.
I'm kind of get up with myself.
All right, no problem. Let's go back a slide. All right. Yeah, so error propagation. We're currently at error propagation, and we're finding the uncertainty of answers, right? Based on calculation. No, you're not able to find the uncertainty of answers, of some of the answers, because because of the calculations, the errors will change. So that's what we're doing in error propagation, right? We say Q is the quantity that we wish to determine, right? And then Q, delta Q is the uncertainty or absolute value of the quantity Q being measured, right? So it's at 0.1 for length, delta Q. Let's say delta Q is length in this case, you'd have 0.1 as delta Q. All right, fractional uncertainty, we'd use this to find our percentage uncertainty. So when you're doing labs, you can have a better understanding of how accurate your results are by using the percentage uncertainty. All right. So we are at the first one. It's very easy, and it's not something that you should really, if you're not understanding, just give it some time and you can practice afterwards, right? But let's just say A is our ruler, the quantity is length. We're using ruler, and our uncertainty, delta A, is 0.1, while B is our triple beam balance, and we're using mass, right? Mass in this case, you would have the delta B as 0.01. You'd have delta B as 0.01. So when finding the fractional uncertainty, you would have the, the, the uncertainty value over the value that you have calculated. So in this case, length is equal to 10 plus and minus 0.1. Remember, we spoke about this in the last time we met. We have an uncertainty of 0.1. We put the 0.1 as our delta L over 10, right? And that would give us 0.01 as our fractional uncertainty. Therefore, this would have a 1% error. So the error for this particular reading would be 1% error. All right, just give it some time. When you're doing the labs, it is mostly used, as I said, we're doing some stuff, some fundamentals, right? Fundamentals for future topics, right? When we do labs, we just want to
So
recap
them,
this. We don't want to reteach or waste time reteaching this. All right, Costa?
so them value. So are you choosing them value?
Values?
Like 10 and 0.1.
These
Just to
these
kind of
are
confuse me.
examples. Is an example.
Oh.
Yeah, when using a ruler,
So
this is actually 0.1. Remember we spoke about this last time, right? For a length, 6.8 centimeters plus and minus 0.1. This is the uncertainty for for um for length when using a meter ruler. Understand?
yes, sir.
Yeah, just give it some time, right? When you're doing the labs, when you're doing labs, you'll go over it over and over again, where you'd get more comfortable with it. We're just going through the regular laws, right? So division, if we're dividing two quantities, right? If we're dividing two quantities, it is the same thing, right? As you realize, it's the same thing. Fractional uncertainty. and this fractional uncertainty, they are the same. All right, for Q, if we're dividing A divided by B, the same thing. You divide the uncertainty of A by the actual value of A, plus you will divide the uncertainty of B by the actual value of B, right? So you use these when we're actually doing labs. We understand here?
Yes, sir.
All right, I am only hearing Jaydan.
Yes, sir.
All right. All right, so I'll take that as we can move on. All right. All right, so the third rule now, when both multiplication and division are involved, the method for determining the fractional uncertainty, it still remains the same, right? You're going to add all of the fractional uncertainties to find the final fractional uncertainty. This should be over Q, right? The fractional uncertainty for Q is the same thing. It's very easy, and you'll get a lot more acquainted with it. All right. I will try and get some exercises so that we can do them and get more comfortable with them. But you see that is the same thing, the fractional uncertainty for A, fractional uncertainty for B, fractional uncertainty for C, plus. It's just plus. The only one that is really different is rule 4. So if K and Ka to the nth power, where K and N are constant, these does not change, right? The maximum fractional uncertainty, right? That is Q, delta Q over Q, right? Is N times the fractional uncertainty for A. All right, so we still see the fractional uncertainty for A coming up again, just like up here. And these other two are constants. You would multiply the fractional uncertainty by the power that it is raised to, right? Which would be N. It's the same thing um if we had a inverse relationship in the power section here, right? If this was raised to say 1/3, it would multiply this by the fractional uncertainty for A, right? Are we okay?
Yes, sir.
All right. No, the last rule, rule 5, if we have quantities, say when quantities are added or subtracted, their absolute errors, right, or their uncertainties, right, will either add or subtract. So Q equal A plus B. If we had some formula in the world looking like this, Q equal A plus B, the uncertainty for Q would be A plus B, delta A plus delta B. And if we had Q equal A minus B, we'd have something looking like delta Q equal to delta A minus delta B. All right, very easy stuff. Okay, are we all clear? I just want to make
Yes, sir.
sure.
I get that. I get
Yes,
that,
sir.
sir.
All right, yeah, we just want to make sure that we have this. You can always go back to them and read over. Yeah, that is the key to passing physics, right? We have to read over our notes when we get them. All right, so note generally a reading may be estimated to half of the smallest division on a measuring scale, for example, a ruler. So the smallest division is 1 millimeters. So this is also equal to 0.1. As we said here, if we had something like this, these are two big ones. And we had, sorry, Let me try it again. Got a big one, some small ones, a middle-sized one, which should represent the half, and some more small ones, and then a big one. Right? So the smallest division here is 0 0.1, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. Right? Now, the uncertainty for this ruler, right, would be estimated to half of its smallest value or smallest division on a measuring scale. All right, so in this case, the uncertainty would be delta L. Let me repeat that again. So this is generally speaking. Most of the times, you will have the smallest division, which will be 0 0.1 divided by 2 to represent your uncertainty. All right. Number 2 says the final consequential uncertainty must always be to one significant figure, right? One significant figure. So the uncertainty cannot be 0.051 or 0.052. That's two significant figures. Remember, one significant figure for your uncertainty. 3 says very often a measurement involves the determination of two readings of the same quantity, right? In this situation, the final uncertainty is the addition. Remember, we see addition coming again. Addition from this law here, the addition of these individual readings. All right, and this table will basically sum up all that we just did, right? You have the sum rule, you have the difference rule, you have the product rule, the quotient rule, and the power rule. All of these, I remember all of these we just went through a while ago. All right. Are we good so far?
Yes,
As it
sir.
relates to error propagation, all right. So now we can move, well, we are out of time. Yeah, we wanted to go into scalar and vector quantities. What time is it now? All right, let me just check the time. All right, so we're out of time for now, right? So we'll go into scalar and vector quantities next class. All right, it's now 1 o'clock. All right, I will try and get you an activity. All right, I'll try and get an activity for Friday, so you can do that in the meantime, and that will cause you to practice errors, give you some practice and errors. I'll try to get it to you by the end of the day. All right, everyone.
Yes, sir.
All right,
Yes, sir.
all the best.
All right.
All right, sir.